Okay guys, so now let's discuss about current amplifiers. So the feedback topology of current amplifiers is a shunt series. So if you take a look at this diagram, so this is a general current amplifier. So here you can see that we have mixed current, the feedback current to this source current parallelly. So that's why we have shunt mixing here, and here we have sampled our output current in series, so that output current goes through this feedback network. So this is the forward amplifier and this is the feedback network, and so this is the equivalent closed loop system. You can see that this is the closed loop input resistance, AF is the closed loop gain, and ROF is the closed loop output resistance. So let's see how we can calculate each of these parameters. So let us start with AF, or the closed loop gain. So closed loop gain in a current amplifier is defined as this output current divided by the input current. So it is I out divided by IS, right? So if we take this uh, using this block diagram, you can see that I out is actually equal to A times I, right? So I'm gonna write I out as A times I, right? And I is actually, if we consider this current going through here is IS coming here, and beta I out current goes through this one. So I is actually IS minus beta I out, right? So this is equal to I out, and I can take this part here and take I out as a common factor. So it will be I out times 1 plus A beta equal to A IS, right? So using this we can easily gain the expression for A by isolating this ratio I naught over IS, which will be given by A or 1 plus A beta. So this is the closed loop gain of a closed loop system, right? So we'll get the same expression here for this current amplifiers as well. Okay, now so let's now calculate the input resistance, the closed loop input resistance, right? So first of all, as before, we need to find out what is the open loop input resistance, that is Ri. So it will be given by, so this voltage here, let me take it as Vi, right? So Ri is Vi divided by II. So this is by the Ohm's law, by applying Ohm's law to this resistance. So let's try to find an expression for RIF. So RIF is here, and in this case the input voltage is again Vi, because you know that this is shunt mixing, right? So voltage across both these current, all these three to these two current sources and this resistor is Vi, right? So taking it like that, so I can write RIF is equal to Vi divided by Is, right? So now I can write an expression for Is in terms of the input current, right? So Vi divided by, so I can write Is equal to II plus beta I naught by Kirchhoff's current law, right? So this II plus beta I out, and I out is actually equal to A times I in, right? So this is V in divided by I plus beta. Instead of I out, I can write A II. So I can take II out from the denominator. So what I get is Vi divided by II, which is Ri, right? So simplifying the expression, I get input closed loop input resistance as Ri, which is the open loop input resistance, divided by 1 plus A beta. So you can see that due to this shunt mixing, the input resistance of this current amplifier has reduced or dropped by a factor of 1 plus A beta, right? So a voltage amplifier, if you remember, the input resistance actually increased due to series mixing. Here, due to the shunt mixing, input resistance has reduced. Okay, then finally output resistance. So you know that when we are finding output resistance, we have to do some changes, right? So first of all, what we have to do is we have to bypass this source. So just simply we can make this current zero, Is, this source zero, right? So we are going to make this Is zero, and also we need to add a source here, right? So I'm going to add a voltage source over here, so it will be producing a voltage of Vx, and which injects a current of Ix into this system, right? So actually I can, sorry, let me make this a current source, right? So current source Ix, and the voltage across this will be Vx, right? Okay, so our output resistance will be given by Vx divided by Ix. So we need to find an expression for ROF, right? So looking at this, this will be Ix2, and I can write an expression for Ix. So Ix is actually going to be the current through this resistor and the current through this resistor. So current through this resistor will be Vx divided by R out, right? And current through the source is A times I, right? So what is I now? So since Is 0, I plus if we write Kirchhoff's current law to this node II plus beta I out, and actually this I out is now Ix. So II plus beta Ix is equal to 0. So therefore II is minus beta Ix. Right? So if I substitute that here, this will be minus A beta times Ix. So I think we have what we need to find the expression. So ROF is Vx divided by, so let me do some changes. So I need to substitute this first. So if I substitute it here, I'll get minus A beta Ix. So I'm going to take it to the left hand side, so it will be Ix times 1 plus A beta is equal to Vx over R out, right? So don't need to worry about this. I think we can get the expression from this right away, right? So what we need is Vx over Ix. So if I take this R naught here and Ix here, I'll get ROF, which is Vx divided by Ix and given by, sorry, R naught times 1 plus A beta. So you can see that due to that uh, series sampling, the output resistance of the closed loop amplifier has increased by a factor of 1 plus A beta. Okay, so let's work out an example in current amplifiers. So this is the diagram of this current amplifier, a feedback amplifier. So this is the current source, and we have a N MOSFET here and a P MOSFET here, and the output current is sent through this laser diode, which is the load, and this is the output current. So we are giving a current and we are taking a current as the output. So, and also if you look at the feedback network, you can say that what is the topology. So here this, using this resistor, we sample this current in series, right? So that means this resistor will generate a voltage here at this point, let's say Vp, which is proportional to this output current, right? And here we can see that this is the input current to the amplifier. So this is the source current, and current through this resistor is actually the feedback current, right? So we are subtracting this feedback current from the source current to give the input current. So this is how it works, right? So there are two additional details that we were given. That is, one is that this RF resistor is very large than 1 over GMN, right? So GMN is the transconductance of this N MOSFET, and also that RF is much larger than Rm. So actually, even though this is not given, we should know that because we are doing a series sampling, so therefore Rm resistor should be small, and since we are doing parallel mixing, Rf has to be large, right? So first of all, we need to draw the small signal model. So I have already drawn it, so to save time. So let's see. So I'll explain this. So here, this is a DC source, so it will be short circuited in the AC small signal model. So it is grounded here, and this is actually the N MOSFET, right? So here in at the gate, it was, this transistor is given a DC voltage. So here, therefore, in the small signal model, it is grounded, right? And this is that current source going from drain to source, so which is GMN times VGS1, but and GS1 voltage is, this is G, this is the source, so voltage is this one. So in this case I haven't drawn this R output resistors because it is a large resistor and we don't need to consider it really because it's very large. But in this is the this is the P MOSFET, and that I have drawn ROP because just since that this is where we get the output current, so when we are finding the output resistance, we might want to consider ROP because it is the output resistance of the this transistor after all. And this is VGS2, and so like that. And so this is the small signal model. So let's see how to calculate values. Okay, so first of all, let's calculate the closed loop gain. So I think the best way to do this problem is to first find the open loop parameter gain and the and feedback factor beta, and use that to calculate the closed loop gain, right? So first of all, let's try to calculate beta. So beta here will be given by the feedback, which is IF divided by the output I out, right? So actually we don't need this model as well, we can even calculate it from here. So that's something that we need to consider here, right? So since this RM resistor is very small than RF, we can actually consider that this I naught does not go through this RF resistor, right? So we can, in other words, we can consider that the current going through this RM resistor is I out, right? So using that assumption, we can calculate, we can write an expression for VP, which is I out. I'll use simple letters here because this is the AC, right? So this is the AC current, so this is I out times RM. So that is VP. So that is coming from this assumption, right? And then we need to find IF, right? So here what we are doing is we are mixing in parallel. So when we are mixing in parallel, you know, due to this shunt mixing, the input resistance will be dropped, right? You saw in the previous calculation also the input resistance of a current amplifier will drop by a factor of A beta. So due to this drop, the voltage at this point, or V in, is approximately equal to 0. That means it's a very low voltage, so we don't need to consider it actually, right? So V in is 0, approximately 0. So using that assumption, I can write an expression for IF. So IF is the voltage across this resistor, which is minus VP. Since this is 0, this is VP, this is minus VP over RF. So VP, I can write it like this. So it is minus I out RM divided by RF. So if I take I out here, I get beta, which is equal to minus Rm over Ra. So this is the feedback factor. So now let's calculate the open loop gain. So when we are calculating the open loop gain, we have to disregard this feedback network. So I'm going to calculate open loop gain, right? So when I'm calculating open loop gain, this if will be 0. So I make if 0 and vp. So I have to ground this point, right? So vp will also be 0. So even if I don't ground this, since this resistance is small, I can consider this point's voltage to be 0, right? And yeah, those are the things, right? So if I do this, a or the open loop gain will be given by I out divided by I in, right? So I in now is now actually is, right? So I out is now this current, right? So remember, now these things are gone, okay? So if I consider this current, I can write that as equal to this. So this will be minus GMP VGS2, that is the output current. And what about the input current? So input current will be this current, right? So this current source. And so let me write it, let me keep it as I in, okay? Yeah. So this is I in current going through this. So I need to find VGS2. So what is VGS2? So VGS2 is actually the voltage across this RD resistor, right? If you consider this, you look at this carefully, it is voltage across this RD resistor. So this, through this RD resistor, the current of I flows, and its voltage is this. So I can write this as I RD. So this will be divided by I. So when I cancels out, our open loop gain will be minus GMP RD, right? Right. So now using these two, we can calculate A or the closed loop gain. So closed loop gain is, so you know, it's 1A over 1 plus A beta. So I'm just going to write the expression. So A is GMP RD. This is divided by 1. So A beta multiplication is plus Rm over F times GMP RD. So that is the closed loop gain. Okay, now let's calculate the input resistance. So calculating the input resistance is very easy actually here. So first of all, I need to calculate the input resistance, the open loop one. So this is the open loop input resistance I'm going to calculate. So again remember that these things are not present, so maybe I erased them, right? So you can, otherwise you will confuse, right? Okay, so like this. So the open loop input resistance is given by this voltage, which is V in, divided by the input current, which is II, right? So let's see how we find it. So V in is here, so I'm going to, now this point is V in and this is ground, so instead of V in I can write minus VGS, right? Because V in will be equal to minus VGS 1, right? And when we take the input current, it will be equal to minus this current, right? So it is minus GMN VGS1. So when minus VGS1 cancels out, the open loop input resistance will be 1 over GMN, right? So using this I can calculate the closed loop input resistance. So closed loop input resistance is, as we calculated before, is equal to open loop input resistance divided by 1 plus AB, right? So that will be 1 over GMN divided by 1 plus Rm over Rf times GMP R. Okay, so finally the output resistance. So when we are calculating the output resistance, we have to make this source 0, right? And also we have to insert a current source instead of this laser diode, right? So can just simply put a current source like this, like that, right? So let's see how we can calculate the output resistance, right? So here, since the source current is 0, so there's no current going in, right? So since there's no current going in, actually this GMNI, so I is 0, so it is equal to this GMN VGS1, right? So since GMN is some positive value, VGS1 is 0, right? So that means that this current is 0. So since this current is 0, this voltage is also 0, right? So this will cause VGS2 also equal to 0. So if VGS2 is 0, this current source also does not provide any current, right? So that means that all these things are not important, right? So the only thing that will be left is this ROP resistor, and which will be our open loop output resistance, right? Because all the other things are not giving any current or what, right? So be Vx voltage across this resistor and Ix current, so it is ROP. So now using this we can find the closed loop output resistance. So it is R out times 1 plus A beta, and we just need to substitute this value. So it is ROP times 1 plus Rm or Rf times GMP Rd. So that's it about current amplifiers.